So like I said earlier, counting all your regular homework and your tests and quizzes and all that, if you end up with an 87, but you did a decent chunk of extra credit homework, I might give you a B plus instead of a B. Right? Not quite an A minus. Yeah. So can't give you that big of a bump, but yeah, a little bit of a bump. That's what I like about the plus and minus grading. It gives me so much more flexibility to actually give extra credit and use it. Right? Okay. So 12.7. If you've looked at it, it's really easy to miss the fact that we actually pretend we're in 4 dimensions to do some of the work. I always try to give you the full concept. I don't want to make it sound like it's crazy hard. We're not going to actually be in 4 dimensions. So let me see if I can build us up to that point. And what we're trying to do here is of a function in 2 dimensions, and I want to figure out a good approximating function for things close to this point here. In fact, you already know, you've taken 280, so you know how to go even beyond this. I can get an approximating linear function by just doing what? I'm kind of giving it away here, right? What can you find? Here's the point AB. And actually, let me be a little more. This is f of A. Cool. So you can find f prime of A, and then just make the equation for the line. Right, so that's kind of like the first thing I like to do once we learn calculus and we learn derivatives. I like to go back and do some algebra problems and show them how easy it is now that we can find the derivative quickly. Right? So that's so what is this? Once I find this function. And this would be like, let's be specific here. Cool. And this is pretty simple. If I put it back into normal terms, this would be like y1, where a is like x1, and this will be the m. So this is just your regular old y minus y1, blah, blah, blah. Written a little more calculus-wise. Right? The cool thing about this is, and you've learned this in your previous calculus courses, this idea extends to even if it's, obviously it doesn't have to be a straight line that we're approximating because we can find its derivative no matter what it is, as long as it's smooth in that area, as long as it's differential. So this extends into 3 dimensions pretty easily. But in 3D, I'm not going to get an approximating line. I'm going to get this, not a tangent line. I'm going to get a tangent plane. It's going to be my approximating plane. And the neat thing is, this problem, this idea, actually sort of applies to that ugly one I gave you on the test where I asked you what's f of -1, -4, and so forth. We were sort of approximating what it would be using the plane. Now, I'm going to make this distinction the same way the book does it, but when we get done with the second way of doing this, I'm going to show you how it's really just a specific part of the first way to do it. So there's really just one way to do this, but I want to show you kind of what the book means. I could describe a surface like this, or I could describe a surface like this. Now notice the distinction I'm making, to be very careful. I don't want to use the same symbol for f, because I want to make it very clear that these functions are not the same. Very obviously, because this is a function of 2 variables, this is a function of 3. So, looking at this, I want to see if you guys are semi with me here. How do I find the trace of some surface that I give you? So there's a problem like this on this test.
Set the third variable.
So that's whatever. So if I want the xy trace, you'll set z equals 0, right? So what if this thing was, this could be looked at exactly as the xyz trace of some 4D w equals f of x, y, z. Because how would you find the xyz trace? You would make w0. So that's the one little thing, and by doing that, it allows me to do the math that I'm about to do. What do we know about level curves and the gradient?
Gradient's
Gradient's got to be everywhere orthogonal to the level curves, right? So if I could bring this down, and the whole idea of a tangent plane, I want it to run tangent to my surface there, right? So if I have this hill here, there's really good pictures in the book. I can never draw one up on the board, although I'm going to try here for some reason. If I'm at this point, I want to figure out what that plane, that's not too bad. That tangent plane is going to somehow contain that, it's actually going to contain all the slopes of all the possible tangent lines coming off of that point. You with me? Because watch this. I could have this tangent line here. I have one color today. Oh. That tangent line there, that tangent line there, that one going opposite some diagonal point, right? You kind of with me? So in 2D, something interesting in 2D that we never really think about too much. I get this. The only other way to go here is this way, right? Mm-hmm. It's kind of silly. We normally think of slope, but you know, a slope is always able to go either way. It doesn't matter. So it has to be the same line no matter which way you go. You with me? So I like to make these analogies that you don't very often hear about. So here, it's got to be the same plane every which way. If you stand at that point, and whatever way you want to go, the tangent at that point, that line has to be in that plane. That's actually the definition of that plane. That plane is the collection of all the possible tangent lines to that point on the surface. That's a kick-ass way to remember this stuff. So, in order to get the equation of a plane, I've already given several of you guys migrants. I'm sorry. In order to get the equation of a plane, what two things do I need?
Point and a vector.
I got a point. It's got to be given to me, right? And the normal vector, which is going to be perpendicular all the way. Interesting. So what? The last little piece we need. We're almost there. The last little piece we need is, here's a level curve, and the gradient at that point, for example, would be there, right? Because like you told me, it's got to be orthogonal. What do you think is true then about a level surface? If I'm in 4D and I make one of the things 0, I'm going to get a surface still. That's a level surface. The gradient has still got to be everywhere orthogonal to that surface. So what's the normal vector that I want at that point? It's going to be the gradient of the function at that point. Because the gradient does what I need it to do, doesn't it? The gradient is going to be orthogonal to all the tangent lines at that point. That's the definition. That's what it does. So if I can figure out this gradient, I'm golden. Just plug that into the plane equation. I'm done. Yes, sir?
What if you did like a cross product between two plane or two tangent lines in that plane?
If you could get two vectors in that plane, then obviously you would cross product it to get the normal.
Yeah, so you could do that too?
Yes, but that's more work. It's quicker to just do the gradient of this, because I've already got it staring me in the face. So let's do a concrete example. That's a pretty good idea, right? Because right now you're all like, what the hell? Let me do just a little bit more. Actually, I'm going to do a lot more. Too bad. Before we get to a concrete example, here's the math behind the process. Okay. And this is You can never say this is cool enough until you actually agree with me, but I don't care. I still think it's cool. If I have a surface, I could certainly have some like curve, and you can think the traces themselves are curves that lie on that surface, aren't they? Traces themselves are curves that lie on the surface. This trace has some kind of definition, some kind of equation. More generally, I can have whatever shape I want to running along this surface. So let's say that, let me see if I can truncate this a little bit. At that point that we're interested in, we're trying to find that plane at that point that contains all the tangent vectors. If I take any smooth curve, C, okay, and it's got to be smooth. And of course, it's got to be smooth. And when I say smooth, I don't mean smooth. I mean, it's got to be differentiable. It can't have any kinks in it, right? That's where a lot of this goes to hell. I can't have a tangent line. Therefore, I can't have a tangent plane somewhere where it's kinky. The plane would just kind of teeter. There wouldn't be a place for it to be.
So it's continuous?
Good. So that's what smooth means. Okay, cool. It's not only continuous, it's everywhere differentiable. Now, stay with me now. What's the equation of that surface? Let me see who's paying enough attention to answer that.
X plus B.
I have no idea what the equation is, but what's the most I've told you so far?
X plus BY.
There. Right? That's the equation for that surface. Is this. That's the equation for that surface. Okay. And we've seen several examples of this, of course. Right? We've seen the examples of ellipsoids and paraboloids and all that kind of stuff. Hyperboloids of 1 and 2 sheets. So that's any of those and more that we haven't even looked at yet. So that's what that is. That's the equation of that. If this lies on that surface, what's got to be true? If I evaluate this at any point on that surface, what's got to be true?
It goes 0.
It's got to be 0. Cool. Okay, how are we doing so far? So I want to make sure we all understand. This is the equation for that surface, which means any point that's actually on that surface has to make this equation true. Yep. If I have some curve that's lying on the surface, some subset of the points on that surface, they all still have to make the stupid thing equal to 0. Of course they do. All right, so far that's not amazing. Obviously, if you want to get a tangent something, line, plane, whatever the hell, right? We won't go further dimensions than that. If you want to get a tangent something, some point I got to take a derivative. So I'll do this side. The derivative of that side is 0. Can you guys figure out what's the derivative of this side? What is, and I like this, I like if somebody would say, it's that. Good, now write it.
Partial of f with respect to x times partial of dt over dx or dt.
I like that. Just the rest of those, right? df, dy, dy, dt, df, dz, dz, dt. Okay. Stay with me now. I can feel like today's lecture is an easy one for me to lose you. I'm glad you're facing here. There's no windows up here. Because me, as a student, I had to sit away from the windows because I would often. Oh yeah, so sure. This is an easy one to do that on. Now, look at that. When you see this, are you guys at the point where you can see a better way to write this using What's a better way to write this, or a different way to write this? What does that look like the result of? Dot product, cool. It looks like a dot product, right? Some piece times another, times some piece times another, times some piece times another. That's a dot product. Comes out to a scalar. So I'm dot producting this vector
Directional derivative.
and this vector.
It's kind of like a directional derivative. Where you have a partial times a vector.
Not really, but sort of. You can almost look at it like that. The problem is this other vector is a derivative itself, not just purely a direction. It's a rate of change.
Okay. Yeah.
But you got the right kind of idea. So what is this piece here?
That's the partial.
Be more careful now. What vector would that be? Let's write it out in vector form.
6 radians.
Yeah. That's the gradient. And I'm dotting it with what vector? Dx, dt. You see if somebody realizes what this is.
Directional? I mean,
In symbols.
the tangent to the.
In symbols, what is it? What's x of t, y of t, z of t? What vector is that? R of t. So what's dx, dy, dz? That's r prime. That's r prime. So this is r prime. And it's being dotted with this guy, which somebody said was the gradient. Beautiful. That's the definition of the gradient. And this equals 0. Okay. So we already kind of discussed the idea. I didn't do any real mathematics. We were talking about the tangent plane being a collection of all of the tangent vectors. And the normal vector would have to be orthogonal to all those. And the gradient does that, right? This, I think somebody said the name of this. What's the name of that guy, basically? Starts with the T. That's the tangent vector. Tangent, this is the, I want you to realize, this is the tangent vector for R. How many R's are on that surface through that point? How many R's are there? Infinite number. So don't get too hung up on that by itself being the answer. It can't be. The neat thing is, no matter what curve I pick, once I figure out R prime, any R prime, I don't care what curve you pick, have got to have this property. They have to be orthogonal to the gradient at that point. So that's why it works no matter what R is. That's why I can write it so very generally. Any smooth curves, there's not some kink thing going on. Okay, so now you're all like, okay, what the hell does that mean, Jeff? So what does that mean? So real quick, the interesting thing it shows you is that the gradient is orthogonal to those tangent lines, like they're supposed to be. So we sort of just proved the thing that we've been talking about for a while. But where can you go from here to get the actual equation for the plate? So what acts as my normal? We already said this, but this is the math that backs it up. What acts as my normal vector? The gradient. The gradient acts as my normal vector. And I have to be given a point. Find the gradient at that point. And then how do you get the equation of the plane from that? So this would be equal to, let's write this in better symbols. This would be equal to f of x at AB, c plus fy at ABC, plus I hat, sorry, plus f of z at ABC. Okay. You with me so far? So the planes are pretty simple. If I want to find a specific plane, I just have to figure out how to find its normal vector and how to find a point. The normal vector in this case was just going to be the gradient at that point. And that kind of jives with what we've been saying. The gradient is orthogonal to. And that's exactly what the normal vector is supposed to do. It's supposed to be orthogonal to everything there. That's perfect. That's exactly what I want. If I know the normal vector, and I know the point, I can just put those two together. Let me make this a little less cumbersome here, so you guys are cool with this. Yes, sir.
Those fx, fy, and fc, those are all the partials.
Partials, exactly. Cool. All right, now let's do a concrete example. So I'm pushing some of you guys past a certain point. I gotta be careful. Let's do a concrete example. Let's just do this here. Yeah. You guys got that? Sort of? Okay. This is where you start to see that this is always true. Trying to get through the derivation. Why do things work the way they work? That's never easy on the first go round. But it often leads to incredibly easy problems. Very nuts and bolts is easy. This is easy. How do I find a tangent plane to anything? I find its gradient at that point. That's my normal vector. And then put it in the right place, and I've got to be given a point, right? These problems are nice. And I love it when that happens. It's kind of weird. It took me forever to freaking explain it. And some of you guys are like, what the hell did he just say? I don't know what the freak he just said. But the actual problem is easy. Can you guys, what's the gradient of this thing going to be? Sorry, let me do this. Oh, the teacher thing. That's F, right? That's F. Always make sure it's equal to 0 in order to do this, because that's what our whole derivation was based on. You got to bring everything over to one side to figure out what F is. Right? Because it's got to be equal to 0 to be that level surface. So the gradient, sorry, you guys were saying? 2x over 9. 2y over 25. 2z. You got 11. It's almost too easy. It kind of is easy to forget. That's really nice just because there were no pairs like x, y sitting next to each other. So they're very separated. The x is only x in it, the y is only, that doesn't have to happen. Be careful. So now, what do I have to do to get my normal vector? Yeah, just figure out what the gradient is at that point. It's going to be, by definition, normal to all of the tangent vectors. That's exactly the thing I want to use to figure out the plane equation. So what is the gradient at 0, 4, 3/5? 0. I like it. Good. 8/25? 6/5. So what's the equation of the plane? Tangent. So my normal vector is that. My point is this. And I just throw the things together. Right? So we get what's in front of this guy? 0. What's in front of this guy? And 8/25, and of course 6/5, z minus 3/5. You guys see that? Yes, sir.
The previous equation you drew up, I think it was on that whiteboard that you covered up. It was partial partial x minus a. Yeah, that's it. Do you plug in the points in for the values a, b, and c? So it'd be x minus.
And that's really what we did. I mean, I like to write it like this because it looks a little more like, and you'll see in a minute, this looks a lot more like y minus y1 equals m times x minus x1, except now we have an additional z minus z1. It's a really nice analogy to make. But in the actual doing of it, to tell you honestly, I would just plug the point into the gradient and then pull off the elements of the gradient to be my coefficients. Let me say that again. Figure out my gradient, which we did here, right? There's a gradient at the point. So what's fx at that point? What's fx at the point? Just looking at this, that's all you gotta look at. 0. What's fy? 8/25, and so forth. So once I have my normal vector, what do I use the components of it for? Coefficients. So when I write it like this, I know it gets a little bit confusing. It almost has to be though. The coefficient will be the derivative in the x direction at this point, blah, blah, blah.
So
But to be honest, all it is the components of the gradient. That's your normal vector. Just take the component out as the coefficient. That's how you build a plane.
Now, is that in unit vector notation?
Where are we at?
The gradient at that point?
No. Yeah.
Does it-
Doesn't have to be, no.
It doesn't.
Definitely not. And the reason it doesn't have to be, and I want you guys to realize this, if I double all of these, it's equal to 0, so who cares? So anything parallel to that, you could throw in here. I don't care. In fact, I don't even like this shit. There's too many freaking fractions in it. Let me multiply everything by 25. I can do it because it equals 0. Who cares? Do you see what I'm saying? So right here, I could have picked, I don't like that one. Let me multiply everything by 25, and I could have used this as my normal vector. You with me? That's beautiful. That's parallel to that. Some scalar multiple. All I need is a direction. The length doesn't matter. And I understand the question. I kind of like that the question came up. The length doesn't matter in this case because the lengths would all just reduce anyway. It's an equation. I would reduce them back down. So see what I get here is 8/25 y minus 32/25. 6/5 z minus 18/25. Right? And that looks disgusting. If I just multiply both sides by 25, that looks a lot better. And look, there's 8 and 30, of course. Right? There's the 8 and the 30. Either I multiply by 25 there, or I multiply by 25 here. I don't care. Technically, you could stop here. Don't. At least bring these in. At least simplify it a little bit. Right? And you don't even have to get rid of the 25s if you don't want to, but it's common practice to do it.
What's the expression for that? R of t is equal to?
And even this could be reduced, huh? I'm sorry, say again. So there's not really, there's no like R of t you could do for this because a plane is a collection of R of t's. So there's not like some uber R of t equation you could throw. That's what this really is. Yes.
The number outside the parentheses, that the equation that you just drew up on the top, yeah. Why is that? I thought it was the partial derivative values, so 2x/9, 2y/25.
Evaluated at the point.
Okay.
Sort of like when you find, let me take you back in time.
Yeah, that's the question.
I don't have a box. It's bigger on the inside than the outside. I mean, just let's talk about what we did before. If I wanted you to find the tangent, find the equation of the tangent line at the point. Let's make it nice. 3, 1. Do you remember these days?
Yeah.
But I want you to realize how the steps we're taking are the same. Almost the same. We don't write things the same in 2D because we don't have to. We actually could do all this work that way.
Yeah.
Don't want to,
It is zero.
right? Over there we have to. Here there's a simpler way to do it because I've lost some dimensions. I can make it a lot more specific way to do it. That's the most general way to do it. It works in a lot of different dimensions. So here, how would you do this? Take the derivative.
X squared over 9. 3x.
Yeah, 3x squared, so x squared over 9.
1.
So now evaluate it at the point 3, 1, and you get the slope is going to be 1, right? At 3, this is 1. Yeah, and then y minus y1 equals m times x minus x1. And I desperately want you to realize we're doing exactly that. We're doing exactly that here. My coefficients are the slopes in that direction. That's what they are. Those coefficients are the slopes in that direction. What was this? Isn't that the slope in the x direction? How y changes as I move x?
So that's a line.
Kinda with me?
That's a line. That's a plane. For you to do it.
Yes, exactly. Cool. How are we doing so far? Semi-decent. I at least want you to realize the math here is not difficult. All right. If you don't understand why things work the way they do, though, you'll forget what goes where. Okay, let's do another one. Let's see. Alex, you have. Oh, let's do this. Yeah, let's do that.
So what did you do with the normal vector? I hadn't copied down all of that.
I'm sorry.
Once you produced the normal vector, what did you do with it?
Then you use those as coefficients.
Okay.
Yeah, the 0, the 8/25ths, the 6/5.
Until you
Yeah.
take it.
Okay.
Let's do this one. So they gave you a point. You're halfway there. The only other thing you need is the gradient, which is going to act as our normal vector, because the gradient is everywhere orthogonal to all these tangent vectors, which is the plane that we want, the collection of all the tangent vectors. Okay, cool. Okay. And this is f here, right? Because it is equal to 0, so be careful. If it's not equal to 0, suck that thing over.
So you get z. It would be.
Yeah, y is squared.
So what's the
Y is
f
squared.
x?
Y is squared. E to the x.
I like it. Because when you take the derivative, that stays the same. The derivative at the top is z. What's fy?
Z to the x.
I like it. And the derivative with respect to z, what sucks about that one? It's going to be a product rule. So if I do the outside first, it'll just be y e to the xz, right? Plus,
yz e to the xz.
careful,
xyz.
I like it. X, y, z, e to the xz. Oops. How we doing? You guys see that? Because when you take the derivative of this with respect to z, x is the constant. It's going to come down. You know, the chain rule thing going on. So don't skip quickly through that part, because everything after that's going to be wrong if you do something wrong here. That derivative is not that hard. So now what's the gradient at 0, -8, -1? Yeah, anywhere that's got an x in the front is going to be 0. There's only one place for that, right? It's too bad for us. Here, the yz squared will be -8 times 1. So -8 e to the 0, so that's just -8. Are we cool so far? E to the 0 is 1. In fact, each of these e to the x, z is going to be 1. Z is -1 times 1, because x itself is 0. And then finally, this piece is going to be 0, right? Because x is 0. And then y is -8 times 1. I like it. The components of that vector will now become my
Your coefficients for the
coefficients. That is the normal vector. I like it. Therefore, its components become my coefficients. So you get -8 x minus 0. That's my point right there, right?
Oh, right. Well, it's -1 minus 1 times.
Minus 1 times y minus,
-8.
I like it, plus 8. Minus 8 times z minus -1, so plus 1. And that kicks ass. That is very like find the equation of the line that is perpendicular to this line and goes through this point. Back in algebra, same thing, except now instead of finding a slope, we're finding a normal vector, which makes sense. It's somehow related to the gradient vector. Those should be kind of related. Yeah, because it is finding a derivative. And then you can clean that up, right? Yeah. -8x minus y is going to be -8 16. I think it's right. Sweet. I like it. Cool. Let me see. I think there's.
Break it a couple minutes.
No, we're gonna leave early, dude.
Oh, okay.
Don't worry. Oh, I like it.
Do you want, Professor?
Yeah.
Do you guys want to set your final equation equal to that constant, or can you leave it -16 equals 0? Does that?
Oh yeah, you can do that. It's in general we like ax plus by plus zz equals b, but it's sort of like in reality y minus y because mx minus. There's no real purpose to simplifying it, but it's convention to put it in simplified form. One last thing I want to ask you guys, and actually this one would be kind of ugly to do this with. Let's go back to the one we did a minute ago, where the gradient. We had this equation. Remember this surface. And the gradient we got was 2x over 9.
2y.
How do you think you find the horizontal tangent plane? For it to be a horizontal tangent plane, what must be true about it?
dy or the has to be.
Don't overthink it, which is obviously the easiest damn thing to do in this class. What's the equation of a horizontal tangent plane?
The dz.
Or just the horizontal plane?
Slope of z equals 0. Slope of z.
Dot product is 0.
Somehow the slope is 0. I agree with you. So that's going to come in.
X, y.
But that's actually going to come out of the fact of what a horizontal plane would have to be.
With the z.
Think about it. Does it hit the xy axis? I mean the xy plane, if it's truly like parallel to it.
Then we're gonna intersect.
It's never going to intersect. So what letters cannot show up in its equations? So give me an example equation of a horizontal
Z
plane.
equals anything.
Z equals 1. And actually what's got to be true then about the x and y? What's like the, let me see how I can say this. What's the normal vector to this plane? Like, this would be 0, 0, 1. How can you see it? What must be in front of the x? 0. What must be in front of the y? 0. What's obviously in front of the z? 1. And in general, to be more general, it could be some constant there. You can always divide by the damn thing, but that's the idea. So therefore, here's a beautiful thing. Here is the gradient. What do you need this to equal in order for it to define a horizontal plane? 0, 0, some constant. So how do you make this equal to 0, 0, some constant? What's got to be true? X must be 0 and y must be 0. Z could be whatever the hell it wants to be. So there's no restriction there. You with me?
C over Z.
Yeah, Z could be C over 2, which is anything. I like it. How are we doing so far?
He says the horizontal asymptote. That's what he said.
Horizontal tangent plane. It's exactly related to finding the horizontal slopes, which sounds like we're headed towards how to do max and min problems, isn't it? Because when you find where the slope is 0, that's a possible location of a max or min. It's a critical point. Oh shit. That's where we're headed now. Is how do we do, and that's why the next section is maximum minimum problems, right? Optimization problems. Alright, so real quick, what point would this be? If x is 0 and y is 0, plug it in. So I get 0 plus I get z squared minus 1 equals 0. So z equals plus or minus 1. So what are the points? 0, 0, plus or minus 1. So at those 2 points, the tangent plane must be horizontal. If you're standing at those 2 points, you're either at the max or the min. You're either at the top of the mountain or you're at the bottom of the valley. I don't know. You semi with me here a little bit. Of course, we just covered this, but the nuts and bolts of this are remarkably easy. Dear God, you should go and read this section. Trust me, you should read it. Especially after lecture today, I'm hoping you see the elements of what I talked about today. You should read this. Yeah?
How did you go from 0, 0, C to Z squared minus 1 equals 0?
From this work, I know that x must be 0 and y must be 0, right? So if I just plug it back in. Don't forget, how do I find a point? Go back to the actual equation that defines the points, right? So plug 0, 0, solve for what z must be. Be careful. Can you always just throw in a 0 in for x and a 0 in for y? No. It's whatever makes the gradient 0 there and 0 there. You with me? Okay. That's plain. That's all I want to do. Okay. Yay! Yay! So see you next time. We'll have a little, I'll finish up 12.7 and we'll do a little quick quiz on 12.7. Not an official quiz.
Oh, okay.
A little quick quiz group work.
I know my backpack is fat.
Sorry. What's up? Yeah. Go ahead. Here. I didn't hurt you.
I think we counted it here. We counted it here, and then we counted it here.
I might.
Here. I made the mistake twice. Thank you.
Calculator. Oh. That's what it's stolen.
Alright.
Is it okay, buddy?
I remember thinking about that.
What? 1 point higher than last time. Or it was 86.
Yeah.
Not an 86. So I guess a 91.
I know it's I don't know why.
How'd you do?
I have a correction. Do you want it? Sure. I just made it.
I understood that. When I was talking about the level curve, if I understood that, I would have easily had an A.
Yeah. That's the one that's
It's such a
Exactly. So, I mean, if we have the 2 plus x in that, then x would be and that would be fine. That plugged in. And then solve for it. You get x plus y here. So then x would have to equal negative 1. Then you have horizontal tangent planes that exist as like a collection of points. Because you can imagine like a shape like this, like a donut. And then the horizontal tangent planes at this line that goes along the bridge. You see what I'm saying? So that's the idea. You can have horizontal tangent line planes at a collection of points, a circle in that case.
So that's in the first and third flag. So if you
Yeah.
illustrate it.
What is my last question? My last question.
You got close.
Is it a projection of the plane? So that
Some people are getting out of it, if you got the pathway there in a different way than what I was thinking.
It's greater than 0. I mean, you cannot, if this was a negative, and this was a positive, it's gonna be a negative, and that's not right.
The actual
And then this should be
For some reason, I think I was just too tired to figure out. Because this is a different way than I was thinking myself.
So yeah.
Yeah, it should go on to the corner where it relates. The 8, let's see, the 8 is actually part of.
plug it in right away, you get 0, 0.
So the way to do it is you project this onto the normal vector and subtract it from the vector itself.
Oh, yeah,
The left
yeah.
part that lies in that plane. That's one way to do it. This could be a different way, you might have just made a little mistake.
This, when you have the addition thing, so you're going from just the
Or this should be
to
a
that
20.
point, so that's what I should, right?
One way to check yourself is, this should be your orthogonal to this,
Yeah.
since this is supposed to lie in plane. So negative 30 plus 10 minus 8 is not 0.
Rating by itself,
And
that's
so,
the rate of change, the maximum rate of change.
that's why that should be 20 to make it the dot product here and 0. So I'm not
So
sure
that's
why.
the difference, this is just your.
At some point you have to tell me what you're doing.
Yeah, you can close it, it's like an answer.
Here's, okay, here's the equation of the plane and vector.
Basically, all, yeah, it's like kind of part of it, but it's just like bended because it depends on the point you're going from at you.
That's the point that the position vector is pointing to. You've got a vector that goes from the point to the plane. That's your normal vector in a way, right? So somewhere you just, actually, it's not a bad way to do it. Which one? Somewhere there's just a mistake.
There are X and Z ones.
In this.
Is that the X?
Yes. Those,
X.
And then this is the Y.
yeah, it goes like that, because you have this, and that. So it's basically there's this.
I'll let you do this, and you can tell me what was wrong here.
Yeah, the ones.
Because I see what your reasoning is, and it actually is a nifty way to do it,
That's
that you think about doing it like this. You kind of created your normal vector in a more generic way, that's kind of cool. But try to see why that didn't come out, because you can see the dot product's not 0, but it should be. Like if that vector lies in the plane, it should be orthogonal to that normal vector, so see if you can see why that didn't come out the way it should.
And the word, just a arithmetic mistake. Do I get right?
I'll give you some point back if you can show me what went wrong. Or a couple points, the 2 points that you were at.
Okay, so here I think you this one? I think I copied it from the calculator one.
No, that's.
Okay.
So you're saying question mark because it was.
Yeah, you had the right
I mean,
expression, but somehow came to the wrong.
I copied it
Okay.
from the calculator. So this is the
I
correct.
like it, cool.
And
I already
for
put
this
on
one,
there, so it's okay there for the correction.
for a hundred, okay. And so for this one, so if you look at it, how can you get x and y greater or equal to 0 if this is a negative and this is a positive? That will never happen if you have a negative and a positive. So you are forced to have a positive, negative, negative.
Exactly.
And that's basically what this says. If you say like x and y, which is defined by x and y, and then that's great.
So I know exactly. So that's what I'm saying. This is not done. You have some explanation or some work to do. Because you're saying what this leads you to, but you didn't actually show me that. So it's sort of like writing a problem that needs to still be done. And I know you could do it, you just didn't.
I mean, but this is the restriction, I mean, you're already restricted, so.
But you understand how I was saying earlier, you could just write x squared minus 4x minus 5, not equal to 0. That is not an acceptable answer, because I need
Yeah,
a
you will have
collection
to
of
factor and
points.
show what you.
I need a collection of points,
Uh-huh.
in that case, values of x, in this case, points, I need a collection of points. This would lead you to it, but it's not answering the question.
So if I just said like their multiplication, or this is and this is, I would have done it.
Or just say where x and y are both the same sign.
Okay, yeah.
Or
that's-
0, yeah.
Well, I wrote it,
I like it, I like it.
And then you
Thank
can
you.
define a point on the point, you can just.
I have just a question.
Yeah.
This was about.
Minus 2.
I would say that that's probably
Oh yeah, so connect that point to say, since the limit changes from different values of n, then it can't exist because it's in 3. So you gotta make that connection. It's not a major thing, but I was taking off for them quiz, so you have to show me that connection. I know what you mean, but you gotta write it out. You gotta explain what that, why that means. Doesn't
Yeah,
make
it's
sense.
because these are supposed to be ellipses,
Just.
so it's like drawing like an ellipse. You're drawing that.
Yeah.
That's
No, but any path you pick has to actually include that point. And neither of those. That's the main thing.
So you use like a different path?
And you don't even use paths, because that is, there's an algebraic method. You only use the two-path method, and actually, to tell you honestly, in this class, you only use the two-path method when I say to. So we're really kind of nice in this sense. So when I say evaluate the limit, that must mean it exists. So you can just plug it in. Yes.
On which one?
Did I do something?
What did you get? You bet.
Secant tangent.
Oh, yeah.
Yeah. Cosecant is hypotenuse.
Yeah, the 36, 37, 36. Right, just square them all, and this would be, 1,
Cosecant
5,
is negative cosecant.
30. Plus 1. Oh, that's good. Okay. Good. Cool.
I have two questions on number one, relationship. With part B.
Part D. So -5, and that was the directional derivative, right? Yeah, okay. Cool, and then here, I think one of these was the wrong number, so now I think it came out. Or you just, yeah, that was what it was. I was trying to figure out what happened, but it just, it should be a plus there, because the negatives cancel, so where it's
Oh,
so it should be
Are they
plus.
on the plus?
So then this will be like
Well, that's
2
good.
point something, this is 8. The difference between those is just under 6.
Yeah.
So isn't it close to the 5 you predicted? It's down 5 because you have to subtract final minus initial. This minus this. To see the real difference, you say where did you end up minus where did you
So
start?
many hours you
I'm having
can-
trouble like
So
visualizing.
we have time to draw.
Really, all it is, I mean, in 2D, it's just that, oh, crap. Get rid of that. In 2D, it's just, if you find a derivative of something at this point, and you say, you know, that means if you take one step in this direction, you should take, y should increase by something close to that rate of change you found. Because the smaller the step you take, the more it should be. And that's just the idea, the more you zoom in on something, the more linear it should become. With me? So if I don't take too big of a step, and that's why I was saying take a unit step, take a step of a length of 1, which could still, if I would have given you a funky function, it could still be too big of a step. But this is kind of a nice smooth function, so not too bad. So you found at this point, at the original point, you found it to be up in 8, right? So my picture's kind of wrong here. So you found it to be 8 here at the original point. And then if you moved in the direction, of course this is all in 3D here, so but if you moved in the right direction, you found that the z actually goes to 2 point something, right? So then this actually did change by about -5 point something. It was close.
Wait, in the y direction?
Well, it's essentially the z. I just don't want to do 3D. Because what you're really doing is, you've got this point here, it's 8, at this given point. And then you move in the direction 3/5, 4/5, whatever it was. So if you move in the direction, and you look at that output, it actually goes to 2 point something. So how much did the z change by? The z changed by about 5 point something. And what did your derivative say at that point? As you move in that direction, your derivative said it should change by about 5 down. That's pretty damn close. The reason it's not exact, of course, is the bigger the step I take, the more the slope changes as I'm moving in that direction. So I'm kind of ignoring that. I'm saying, let's pretend the slope is always this, when in reality the slope is changing as I'm moving, right? So it's never going to be perfect, but it should be close. And that was one where it actually comes out pretty damn close. I like that problem because it's nuts and bolts. You can chug it in the freaking function and look at it. Derivatives are more theoretical, right? But this is kind of checking it out. Is it close to what it said it should be? And of course, the smoother the function, the better it's going to be.
Alright, and then the last one was for this one. You just wanted to explain it in words that it's needed.
Oh yeah, tell me something. You could say right here at the end of the dot product, so since it's not 0. And then they're not scalar multiples of each other, so yeah, cool.
What?
That's why I'm there, man. Please, yes.
It's not even that bad of a grade, but I know
Could be better. Yeah, I did expect higher than that.
yeah, that's a, well, I did because I know, my study habits.
Well, I mean, compared to what I think you are capable of, from what I've seen you do in the past, I thought you could do better. Yeah. So certainly, man, come out to office hours, do your homework, and ask me questions. That's the whole reason I'm there. Cool.
Thank you.
Well, let me try this dude. I'm getting all this.